Hello and welcome to this video on Python Standard Library. We have already covered bytes and byte array in our previous videos, so we proceed with memory view. Now we will go through the documentation first, and towards the end I will show you an example as to where and how to use memory view for its benefit. It's a very unique thing, and the benefits of memory view will be shown at the end. So let's get started. So what memory view does is that it allows Python code to access the internal data of an object that supports the buffer protocol without copying. We have already seen buffer protocol, and the important part is without copying. We'll see the benefits of not copying the object when we look at the example. Now, the class name is memoryview. It takes an object. The object must support buffer protocol. So the buffer protocol supported objects are like bytes or byte array. Similarly, array.array also supports buffer protocol. So it says that a memory view has the notion of an element, which is the atomic memory unit handled by originating object. For many simple types such as bytes and byte array, an element is a single byte, but other types such as array.array may have bigger elements. For example, an array.array may have Unicode. Length, when you use the length function on view, it is equal to the length of toList. This is a member function we will see in just a bit, which is the nested list representation of the view. If view.endIm, that is number of dimensions, is 1, this is equal to the number of elements in the view. Now number of dimensions if 0, then it will raise a type error. Item size attribute will give us the number of bytes in a single element. A memory view supports slicing and indexing to expose its data. One-dimensional slicing will result in a subview. So suppose we have a byte array element like this, or rather bytes. Then you pass it to the memory view constructor, and you will have a memory view object. So you can do the indexing because it supports indexing, and we get the output. Now if you slice it, then you get the subview. Now you can convert that back again to bytes to get the elements. If format is one of the native format specifiers from the struct module, indexing with an integer or tuple of integers is also supported, and returns a single element with the correct type. One-dimensional memory views can be indexed with an integer or one integer tuple. Multi-dimensional memory views can be indexed with tuples of exactly ndim integers, where ndim is the number of dimensions. Zero-dimensional memory views can be indexed with the empty tuple. So for example, consider an array where these are the elements. You make a memory view out of it, and then you index it, and you take the step by step. You have a stepper of 2, so the first element and third element will be part of the sliced memory view, and you can convert it to a list, which will give you these 2 elements. If the underlying object is writable, the memory view supports one-dimensional slice assignment. Resizing is not allowed. So consider a byte array. You convert it to memory view, you check the read only, it is false, so you can supply v0, you can assign to v0 z, and then you will see the data is byte array zbcef. So when you change the 0th element of memory view, the data is changed. Similarly, you can do assignment on the slice. So you can assign 1 to 3 to the slice 1 to 4, and it becomes z1 to 3 fg. Okay. Now if you want to assign to 2 and 3 the value spam, the structures are different, the size is actually different, but you can do assign 2 to 6 and you assign spam. So it will become Z1 as spam. One-dimensional memory views of hashable. Hashable means read-only data structures. Types with format capital B, small b, or C are also hashable. The hash is defined as hash of m is equal to hash of m2 bytes. So we have a byte array A, B, C, E, F, G, and we check if the hash of the memory view with the bytes is equal or not, then it is true. Similarly, if you take the hash of the slice of memory view to the byte array, it is true, and so on. There are several methods which memory view have. One is underscore eq underscore, which is the operator overloaded for equality operator. So if their shapes are equivalent and all corresponding values are equal, then the equality operator will turn out to be true, and the operand's respective format codes are interpreted using struct syntax. For the subset of struct format strings currently supported by toolist, v and w are equal if v.toolist is equal to w.toolist. So we have an integer array 1, 2, 3, 4, 5. We have a double array 1, 2, 3, 4, 5, and we have a byte array 5, 3, 1. We convert two memory views. X is equal to memory view of A and Y is equal to memory view of B. Now we compare if X is equal to A is equal to Y is equal to B, which is true. And consequently, the two list will also be true. Now we create another Z with taking the slice of Y with the step 2, that is 1, 3, and 5. Okay. Sorry, minus 2 is there, so it will become 5, 3, 1. So Z will become equivalent to 5, 3, 1, that is C, and the two list will also be equal. If other format string is not supported by the struct module, then the objects will always compare as unequal, even if the format string and buffer contents are identical. So consider this: we have imported big Indian structure and C underscore long from C type, and we have declared a class BE point which inherits big Indian structure, and fields are X and Y of type C underscore long. Now we create a class of we create an object point from this class by passing 100 and 200. Then we create two memory views. A is equal to memory view point and B is equal to memory view point. Now A is neither equal to point nor A is equal to B. So note that as with floating point numbers, V is W does not imply V is equal to W for memory view objects. There is a function which is 2 bytes, which returns the data in the buffer as a byte string. This is equivalent to calling bytes constructor on the memory view. So we have a memory view for byte array ABC. We call 2 bytes, which is equivalent to calling bytes on the memory view. For non-contiguous arrays, the result is equal to the flattened list representation with all elements converted to bytes. 2 bytes supports all format strings, including those are not in struct module syntax. Now in version 3.8, it is added that order can be CFA. When order is C or F, the data of the original array is converted to C or Fortran order. For contiguous views, A returns an exact copy of the physical memory. In particular, in-memory Fortran order is triggered. For non-contiguous views, the data is converted to C first. Order is equal to none is same as the order, same as order is equal to C. We can also convert it into hex. Okay, it has a separator and bytes per separator are 2 arguments, so you can experiment with those. Here a memory view is created and the hex value is printed. Now a chain in 3.8 is similar to bytes.hex, and memory view.hex now supports original sep and bytes per separator parameters to insert separators between bytes and in the hex out. ToList converts the data in the buffer as a list of elements. If we have ABC and you convert it to ToList, the byte values of those will be shown. So similarly, if there is a double, then array of double, then we have 1.1, 2.2 and 3.3 as members. We convert it to memory view, and when you apply to list to it, it gets converted to a list of 1.1, 2.2 and 3.3. And 3.3 to list supports all single character native formats in struct module syntax as well as multi-dimensional representation. To read only will return a read only version of the memory view object. The original memory view object is unchanged. So that means you cannot apply the assignment or the slice assignment to the read only memory object, memory view object. So here we have a byte array, and then we have memory view of that. We make that read only, and to list will work, but you can't assign. Okay, but you can still assign to the original memory view, and we can get the to list version. Release method releases the underlying buffer exposed by the memory view object. Many objects take special actions when a view is held on them. For example, a byte array would temporarily forbid resizing. Therefore, calling release is handy to remove these restrictions and free any jangling resources as soon as possible. After this method has been called, any further operation on the view raises a value error except release itself, which can be called multiple times. For example, we have a memory view of ABC, we call release. Then if you try to get a value out of that memory view, it will cause a value error. So with the memory view ABC in M, we have M0. So now after this, you can't get this M0 because memory view has been released. Once it goes out of scope, the release will be automatically called. Cast method casts a memory view to a new format or shape. Shape defaults to byte length. W operator by new item size, which means that the result view will be one-dimensional. The return value is a new memory view, but the buffer itself is not copied. Supported casts are one-dimensional to contiguous and contiguous to one-dimensional. The destination format is restricted to a single element native format in struct syntax. One of the formats must be a byte format. The byte length of the result must be same as the original length. Note that the byte length may depend on the operating system. So we cast one-dimensional divide by long to one-dimensional divide by unsigned bytes. If we have an array of long 1, 2, 3, we convert it into memory view and we get the format. Format is long, item size is 8 bytes, length is 3, number of bytes is 24. Now we cast it into bytes. So format is bytes, item size will become 1 and length of y will be 24 and number of bytes will be 24. From one-dimensional unsigned bytes to one-dimensional char, we have z, y, z. We make memory view out of b, that is x. To the first element, we try to assign byte of a. So it has invalid type for format bytes. Now what we do is we cast it to character and then we try to assign, it works, and then b becomes byte array a, y, z. Again cast from one-dimensional bytes to three-dimensional ints and to one-dimensional signed char. So suppose we have a struct, we pack I 12 times and then we have a list of range 12. We convert the buffer to memory view and we cast it to integers with shape 2 to 3. So it becomes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. When the format is integer, item size would be 4, length of y would be 2, y of n bytes would be 48, and then we cast it to bytes. The format becomes byte, item size becomes 1, length will become 48, and number of bytes will be 48. One important thing to remember here is these integers are 4 bytes because they can fit in 4 bytes. If you supply very large integers, the item size will not remain 4 and number of bytes will not remain 48. It will increase if you supply very large integers. Similarly, we have one-dimensional unsigned long to two-dimensional unsigned long, which you can read for yourself. Then we have obj, which returns the underlying object of memory view. So the underlying object in this case is bytes, so which is true. n bytes gives the shape into item size, that is length of n dot 2 bytes. So we have already seen this. Read only we have seen. Format is a string containing the format in struct module style for each element in the view. A memory view can be created from exporters and arbitrary format string, but some methods to list are restricted to native single element formats. Format B chain in version 3.3 is now handled according to the struct module syntax. This means that memory view bytes of ABC element 0 is equal to bytes of ABC 0 is equal to 97. Item size gives us the size of each element in the memory view. Endim is number of dimension. Shape is the tuple of integers of length endim, giving the shape of the memory as an n-dimensional array. An empty tuple instead of none when n-dimensional is 0. Strides is a tuple of integers, the length of endim, giving the size in bytes to access each element for each dimension of the array. Sub-offsets is used internally for PIL style array. The value is informational only. C underscore contiguous tells us whether the memory is C contiguous or not. F contiguous is Fortran contiguous, and contiguous is contiguous. So we have seen various uses of memory view, but the real kick is not all this. As such, you don't find these operations very useful, but I will show you an example where the memory view is very useful. Now, to look at, before we look at the example, I will show you 2 points here. That is, if you look at them carefully. The one thing is that it does without copying, okay, access the internal data of the object without copying. And second is it supports slicing. Indexing is always a one operation. Thing is slicing. Now, if you slice a sequence like a string or something immutable, then a copy is made. But if you slice what we call a memory view of that object, then copying will not be involved. So the first example is trivial. We have an array of Unicode. So in this case, item size would be 4. So let's hit the terminal, and if you see Python memoryview.py, it tells you that the size of these is 4. But that is not the example I was talking about in the beginning. The example is this one. Now consider you are writing some code where you need to make these slices a long number of times. For example, in AI application, it could be quite common to have such large number of iterations. So we have the value of n as 100,000, 200,000, 300,000, 400,000. We create a data object of x so many times. We start the time. To measure how much time it takes, we assign the data to a value b, and then we start the slicing, and finally we print the number of finally we print the time, how much time it took. And similarly, in the second loop, we have memory view of the data object, and we perform equivalent operations. Now I'll run this and you will see what is the difference in timing. So because it takes it creates a copy, the first version compounds quadratically, but the second version compounds linearly. Okay, so this is the benefit of using memory views. When you have to slice for a large number of iterations, you can make of the use of the memory view, provided your object supports the buffer protocol. In general, you would want to slice something like a string, which is a read only, and copy will be involved. Objects which do not make copy on slicing do not need to go through this. So this is the example of memory view, and it shows that how you can get high performance with memory view objects when slicing a large number of times. So with this, I'll stop here, and in the next video, we will talk about sets and Trojan sets, and we'll see how much we can cover. So thanks a lot for watching the video. Have a nice day.